Hello, everyone, and thank you for attending today's webinar, How AI Research is Enabling Next-Gen Codecs. This webinar is brought to you by Qualcomm and is a continuation of our webinar series on AI. My name is Pat Lawler. I'm a staff manager in technical marketing at Qualcomm Technologies, and I'll be the moderator today. Before we get started, I'd like to go over a few housekeeping items. At the bottom of your screen are multiple application widgets you can use, including a widget to download today's presentation. All the widgets are resizable and movable. The slides will advance automatically throughout the event. At this time, we recommend you disable your computer's pop-up blockers. This will allow the slides to advance automatically. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A widget and then click the Submit button. We'll answer questions after the presentation. Also, if you're experiencing any technical problems, please type your issue into the Q&A widget and we'll be glad to offer assistance. I would like to now introduce our presenter for today. Taco Cohen is a senior staff engineer at Qualcomm Technologies Netherlands and part of Qualcomm AI Research. Taco, please take it away.
Thanks, Pat, and thanks everyone for joining. So I'm going to be talking today about how AI research is enabling next-gen codecs. I'll go over all of the research that we've been doing to use AI to improve compression. So first, let's have a look at the agenda for today. So first, I'll start by motivating this work. Showing a couple statistics on how the demand for improved data compression, in particular video compression, is growing exponentially. Motivating the improvement of this kind of technology. Then I'll show or argue that AI is a compelling tool for compression. More specifically, machine learning and deep neural networks are very promising in this regard. I'll show some results from our latest research on voice and video codecs using neural networks. And I'll give a demo of our latest on-device neural video decoder demo. Then I'll talk about some future research and challenges ahead for this type of technology. All right, so first of all, the scale of video and voice being created and consumed is massive. Here's a couple of stats. 1 million minutes of video crossing the internet per second. 82% of all consumer internet traffic online is video, whether that's FaceTime or Netflix or YouTube, etc. 76 minutes per day, that's the average for US adults for watching video on digital devices. 8 billion average video views of Facebook, 15 billion minutes of talking per day on WhatsApp. So I guess we all know increasingly video is all around us. It's providing us with entertainment, enhancing collaboration, very important, of course, during this pandemic, and transforming industry. You can think about use cases like a smartphone video. We can all record and watch video anywhere right now. Sports, video conferencing, autonomous vehicles, where not only does the autonomous car have to see the world around it using video cameras. Very often this data also needs to be transmitted to a central server for training purposes. Think about smart factories, extended reality, smart cities, video streaming, the list goes on. Now, video technology has a very long history. Here we see a nice old-fashioned picture from one of these, I think it's a cathode ray tube TV, big box, small screen, and clearly we've come a long way since then. We can now watch video anywhere. Resolution is much higher, and of course that is enabled in large part by better compression technology. So here's a bit of a timeline. one of the early codecs, MPEG-2, released in '95 onto 2003 AVC or H.264, and more recent codecs like HEVC, H.265, and the latest versions EVC and VVC. And you can see that with each generation, with a cadence of about 10 years in between, each generation brings new features. Most recently, things like 4K resolution, high dynamic range, 360-degree video, and very latest 8K. Probably your TV doesn't support it yet, but it's coming. Immersive video, etc. And aside from new features, also every generation tends to bring about 50% improvement in compression, meaning you have to spend 50% fewer bits to get the same video quality. And in total, all this work over many decades has brought us to a point where now we can compress video by a factor of about 1,000 relative to a naive storing of all the data. So that's absolutely massive reduction, and you can see how clearly this technology is essential. Without it, all of the technologies I mentioned before, all of these use cases would not be feasible. But we don't think this is the end of the line, of course. We think more improvements is possible. So visual quality has a number of factors that play a role there. So first of all, there's the pixel quantity, the resolution, of course, and the frame rate. These are going up. But also things like pixel fidelity, the color accuracy, contrast, and brightness are very important to the perceived quality of the image, and that's why these features, like for example HDR, are so important. All right, so now we get to our work on AI, and in particular our research on deep generative models. So generative models are a fundamental technology based on deep neural networks that have a really wide range of applications. So the basic idea of generative modeling is to take some training data set, usually unlabeled. So for instance, could be a collection of images, and we train a model to learn the statistical patterns in this data set, and thereby be able to generate new samples from the same distribution, samples that look the same or similar as those in the training set, although not identical. I'll explain how we can use this for various applications in a minute. Now, there are a number of types of generative models, like the variational autoencoder that we'll rely on heavily, and I'll explain in a minute, as well as generative adversarial networks, autoregressive models, and invertible or flow-based models. What's common between these things is a couple powerful capabilities. So first of all, the ability to extract features by learning a low-dimensional feature representation. So basically, we extract from a particular image or video, we extract the essential features, which are easy to transmit, low-dimensional, and from that we are able to reconstruct the original. You can use then this sampling to generate or restore or predict or compress data. So number of applications, as I mentioned, speech and video compression, where you would not generate the data instance, whether it's image or video, out of nothing, as in pure generative modeling, but you would use something called a conditional generative model, where you condition on the bit stream that's being transmitted, and then you generate a likely image or video that could have been the input of the encoder. In text-to-speech, you also use a conditional model, but in that case, you condition on text. And the task of the model is to generate an audio signal that is most likely, or at least likely, to correspond to that piece of text. It's used in graphics rendering in various ways, for instance, in super resolution, computational photography, and other voice UI applications beyond text-to-speech as well. So the main kind of model, as I mentioned already, is something called an autoencoder. So this is what we'll be relying on throughout this talk. So it's an important concept to understand. So an autoencoder in the most basic form consists of two neural networks. One is called the encoder and one is called the decoder. So the encoder takes as input some piece of data like an image or an audio fragment or a video. It uses some neural network that typically has an architecture that's adapted to this kind of data, suitable for processing, say, temporal sequences or spatial images or something, or whatever the data may be. And this encoder will output something that we call latents or features. And these are computed from the input using the neural network, and they are supposed to capture the most important information about this piece of data. This latent representation can then be quantized and compressed into a bit stream, which can be transmitted. And then on the receiving side, there's a decoder neural network which takes these quantized latents and feeds them through another neural network to try to reproduce the input as closely as possible. Now, in the variational autoencoder, which is fundamental to compression, there's actually a third component called a prior, which tries to predict the latent representation. And using that model, it's possible to losslessly compress the latent representation to squeeze out any redundancy that may be left there. So we think that this AI-based compression has a whole list of very compelling benefits. So the first one is, of course, improved rate distortion performance. So rate distortion is the fundamental metric for compression. You want to use as few bits as possible. You want to lower the bit rate while minimizing the distortion. What we've seen so far is that these neural-based compression methods are at least very promising. In some modalities like voice compression, we already greatly outperform classical codecs. And in the case of video, the comparison is more difficult to say what is a fair comparison. In some cases, we are a little bit worse. Some cases, we are better. But the rate of improvement of the neural codecs is extremely fast. So we're very optimistic that we can improve the rate distortion performance. It's the most fundamental aspect. Now, another very interesting feature is that a neural codec can be specialized to specific data distribution. So if you develop a classical codec, that takes a lot of work, and it requires the classical codec has to be standardized. So this happens, as I mentioned before, only once every roughly 10 years, and that means that you can't specialize your codec to a particular type of data. It has to work for all, let's say, video. If you are building a self-driving car that will only ever see road scenes, you can't make a codec that's very good for that. The best you can do is maybe tune the encoder a little bit, but the decoder is standardized, so you can't change it. On the other hand, for a neural codec, all you have to do is retrain the neural network on some new data set, whether that's sports videos, whether that's images or videos from a self-driving car or some other specific type of data. And you can expect to improve the performance in this way. Now, a further benefit is that whereas classical codecs typically require hardware acceleration, this is a bit different for the AI-based compression methods. So in particular, although a neural network needs to run on special purpose hardware, it doesn't have to be special purpose for neural compression. So currently in Qualcomm hardware, there's already subsystems that can process neural networks very efficiently, and that's really all we need to run an AI-based compression system. So one implication of that is that neural compression methods are very easy to upgrade. So whereas with a classical codec, you need to first gain a consensus in the whole industry on what the next next standard is going to be. Then hardware needs to be developed and deployed and so on, which causes this very long 10-year iteration cycle. In the case of neural compression systems, in principle, any company or individual can unilaterally decide to develop a better codec. Perhaps it's only better for their particular applications, but in any case, they develop their own codec. And as long as it can run on this fairly general purpose neural accelerators, they can deploy it. Another advantage is that neural networks can understand what's in an image. So they're aware of the semantics. In fact, that's one of the main reasons why neural networks and AI became such a buzzword. Neural networks are very good at recognizing objects in images. So we can use that in compression by making sure that the encoder, emphasizes the semantically important parts of the image. So, for instance, as human beings, we typically care more about humans in images rather than, say, some detailed texture of water. So if our neural network can recognize the different semantic classes in an image, we can then train it to give lower distortion and perhaps pay more bits for the semantically important regions like people, and less bits for the less important regions. We can also fine-tune our codec for a particular perceptual quality metric. So classically, codecs are evaluated based on the PSNR metric, which is okay, but it doesn't align perfectly with human judgments of perceptual quality. There are, however, better metrics, and for a neural codec, all you have to do is change the loss function to use this perceptual quality metric as a distortion metric, and just retrain. You wait 1 week, and you have a model that's optimized for this kind of metric. Then there's the benefit that AI-based codecs can generate visual details that are not in the bit stream. So whereas a classical codec, if you continue to reduce the bit rate, you will eventually start seeing artifacts, things like blocking and blur artifacts and other kinds of artifacts. With a neural codec, in principle, it's possible to have the neural network essentially imagine the details that could have been there. So you can try to train this neural network to always output something visually pleasing, something realistic looking, even if not all the details are in the bit stream. So perhaps there's some texture of grass or water or something like that, and the model will recognize that there is this kind of texture, there is grass here, there's water here, but not send all the details about every individual pixel. But the decoder will be able to, it has experience, it has seen a lot of grass textures before, a lot of water textures, and it will be able to, generate something that looks visually pleasing and semantically doesn't change the image too much. And finally, we think that it's relatively easy to develop new codecs for new modalities, things like point clouds, omnidirectional signals, and other kinds of new signals. And the reason is that we've been researching this topic for a relatively limited amount of time with a relatively small team. The video codecs have been developed for several decades by thousands and thousands of people across the industry. And we're, in terms of man hours, we spent much less, and still we're already on par, if not better, than the classical codecs. Part of the reason for that is that with the AI-based approach, a lot of the improvement is essentially done for us by the learning procedure. All right, so that's some of the benefits, some of what motivates our research into this topic. So let's look at some of our research and our results. So first, I have one slide on speech compression. So here's a sketch of our neural speech compression system, or rather, a part of that system. The input in this case is a spectrogram representation of the speech signal, Again, as I explained before, there's an encoder neural network. In this case, it's a convolutional type network that outputs a number of these latent variables, which are quantized, in this case using a code book, and compressed, then on the decoder side, decoded to try to reproduce the spectrogram. Spectrogram is then turned into a waveform by another system. Now, the headline figure here is that we reach roughly 2.6 times improved bitrate relative to the state-of-the-art classical compression method at the same audio quality level. So that's I think quite a drastic improvement that we've shown here. That really highlights the promise of this technology. Then we have a lot of research on video compression using neural networks. So here you see a typical architecture that we use for this type of data. So you see on the left, you see a video sequence, in this case 3 frames. And the first frame is compressed using something called an iframe neural network. So it compresses this frame independently of any other frame. The image goes into the encoder. Again, that's a convolutional network. It outputs some latents, which are compressed in a lossless way using entropy coding. This gives you a bit stream, which can be sent over the internet. Goes into an entropy decoding procedure to produce the latents that were produced by the encoder. They're identical. And then the iframe decoder will try to reproduce the images as well as possible. So that's the iframe. That's the top row of this figure. What we then do is we take the second frame, and first we compare it to the reconstruction of the first frame using something called motion estimation. So we basically estimate for each position in the image how it moved. This information is then fed into the P-frame encoder, which again produces a bit stream that's entropy coded, decoded, fed into a P-frame decoder. So now the P-frame decoder outputs 2 things. Firstly, it outputs this motion field shown at the top output of the P-frame decoder. This is then used to warp the previous reconstruction, which gives you some estimate of the frame at time t=2. And the P-frame decoder also outputs a residual. The residual is the difference between the prediction and the actual frame, or at least an estimate of that. This residual is added, and that gives you the reconstruction for the second frame. This procedure is then repeated a number of times. The whole thing is trained end-to-end to minimize the rate, so the length of the bit stream, and the distortion, so how close the output frame is to the original frame. More recently, we've been investigating different kinds of GOP structures. So GOP stands for group of pictures, which can have various structures, as shown in this slide. So first of all, there's the iframe approach, where basically you take every frame and you just independently encode it as an image using an image compression system. Now, this is very inefficient because the different frames are very, sequential frames are very similar to each other. So you want to exploit that redundancy as we showed on the previous slide using some prediction mechanism. That's what the P-frame codec does. It sends first an iframe that can be compressed independently, and then it sends P-frames, meaning predicted frames, where each frame is predicted based on the previous one. And in between, you might sometimes intersperse iframes so that you can easily skip through the video at random points. The best approach, however, as we know from classical codecs, is to use B frames as well, which are frames that are predicted not just from frames that are in the past, but also frames from the future of the video sequence. Of course, those frames from the future have to be sent first, but by knowing both where the video, what the frame looked like a while ago and what it will look like in the future, it's more easy to predict the frame in the middle, than just using past information. So this is a very effective approach, but until recently, this had not been applied to neural compression, or at least most of them were using p-frames. So we started to investigate this, and here we see, first of all, our existing p-frame codec, where we have some input. There's a motion compensation component that uses the reference, as you see on the left, and predicts the next frame and compresses the residual. Then there are different approaches to B-frame compression using neural networks. So the first one is based on bidirectional motion compensation. So in this case, you just have two references, one from the past, one from the future, and you just estimate a motion field for both of them. You compress both of those, and you let's say predict the frame in the middle by averaging the predictions. However, those motion fields, they will tend to be collinear because things tend to move in a linear way over small periods of time. So they're very correlated. You're essentially sending very similar motion fields twice now, which is costly. Then there's another approach which is based on frame interpolation. So here what happens is you have the two reference frames and you try to interpolate between them. And that just gives you your prediction. So there's no motion field involved. You just interpolate the frames. And that gives you a prediction for the next frame, which you can then add a residual on top of and generate an output. But this interpolation approach doesn't work very well for large motion. So what our B-frame codec does is very simple. Again, you have two reference frames. You first apply frame interpolation to try to produce not a direct prediction of the next frame, of the B frame, but a new reference frame. This reference frame is then used in a standard P-frame codec to compress the image. So the P-frame codec will take this interpolated frame, warp it using a motion field that's estimated, and add a residual on top. And this, we've shown that this works very well. Here's a graphical illustration of how this works. So we have here an input, xt. It's here shown as a one-dimensional signal rather than a two- or three-dimensional one as in image or video, but it's one-dimensional signal, and we see the blue dot. Let's say that's a particular pixel. Then let's skip ahead. So what you see here is, first of all, motion compensation. Using a green arrow, we say where will this pixel go, this reference pixel go to produce prediction of the current pixel in the current frame xt. Then you see in the third column, you see what happens with bidirectional motion prediction, where you see the two arrows are almost collinear. So there's some redundancy there. We're predicting the center pixel from the reference frames on the left and right. Motion interpolation is shown in the fourth column, where we're just interpolating between the two blue dots to produce the dot in the center. But as you can see, there's a gap. It doesn't accurately predict where this pixel will go. So our approach shown on the right will first do the interpolation, produce a reference frame, which is then corrected by motion compensation and residual. So here we show some results using two metrics. One is PSNR, which is the classical and most trusted metric, and then there's MSSIM, multi-scale structural similarity, which is an attempt to produce a metric that better aligns with human judgments, although this metric also has some blind spots. But the overall picture is pretty clear. You see in red the H.265 rate distortion plot. And there's a Google neural compression method and our method, which outperforms both of them. To read this kind of graph, what you want is that the curve is as close as possible to the left and to the top, meaning at every bit rate shown on the x-axis, you want to reach as high a value of PSNR, meaning as low as possible distortion. So the curve, the blue curve being on top, means it's doing better. Okay, then we have another research project, which we call instance adaptive compression. So I already mentioned the adaptiveness of neural compression approaches, meaning you can train your compression system on a particular kind of data and improve it for that kind of data. Now, in this project, we take this to the extreme by fine-tuning or overfitting our model on a particular video. So we have one video, or could be one image, and what we do is we train our model to be able to compress this particular video as well as possible. Now, of course, if you do that when you're encoding a video, you're going to need that overfit model to be able to decode the bit stream produced by it. So in order to be able to use this kind of system, this kind of overfit model, you also have to send it over to the receiver, which is done by sending some what we call weight deltas. So for each weight or parameter of our neural compression model, we send a delta to the receiver. That allows the receiver to know what this overfit model looks like, and then it can interpret the bit stream produced by the overfit model. And we've shown that, again, we can get quite drastic improvements using this kind of method, where, again, here you see clear gains in terms of rate distortion for our method. Some headline numbers: we get 24% improvement in BD rate, which measures sort of the overall improvement in bit rate at the same quality over the leading neural codec by Google. 29% over FFmpeg implementation of H.265. And another cool thing about this is that it enables mobile-friendly deployment, because whereas a video compression system that has to work for any video has to be quite large in order to understand all the possible visual details that could occur in a video, this overfit model actually only needs to know the visual details that are part of this particular video. And so we've shown that we've been able to reduce the complexity of this neural network by 72% while still maintaining state-of-the-art results. All right, another project is about variable bitrate image compression and ultimately video compression, which is very important. Most of the neural compression methods so far have just trained one model per quality level or bitrate level that they wanted to target, which has many practical downsides. So that's what we call a level 0 system, where we have one model for every quality level. Requires a lot of training, and also at deployment time, this is not very practical. So then we have a level 1 system where we have a single model that's trained to output multiple bit streams depending on the quality level desired. And this is done by inserting on the encoder and decoder side quality indicators called data. And finally, there's a level 2 solution where you have a single encoder that outputs one bit stream, and by cutting short this bit stream, you can send the same image at different levels of quality. Now, level 2 solution is harder than level 1, is harder than level 0 to develop, but also has increased ease of deployment. So we apply a technique called latent scaling in order to achieve variable bitrate for a level 1 approach. So I'm not going to explain this complicated diagram in the interest of time, but the basic idea is to insert a scaling factor S that can be used to essentially coarsen or make finer the quantization grid that is applied to the latent variables, and that will allow, the information to be transmitted with higher or lower fidelity. There's a second part to our approach that will enable a level 2 solution called nested quantization, where the first part of the bit stream represents a coarse quantization of the information, and the subsequent parts of the bit stream will gradually refine this information. And we've developed a technique to do that without much loss of, without incurring much bitrate overhead. So here you see the solution. I hope it's somewhat visible, but as you can see, our scheme produces a single bit rate, and depending on how much of the bit stream produced by this model you send, you will get different quality levels that are actually competitive with the quality levels that you would get from, say, HEVC. We've then extended this to a semantic aware image compression system. So the idea here, as I mentioned also before, is that we want to spend more bits on regions that are important to people, like the person in this image, and in particular the complicated textured regions like hair and the shoes and so on, and less bits on background. So to do that, we take these scaling factors and we don't apply them uniformly across the image, but we make them spatially dependent. So in order to do that, we've added one component to the network. So as usual, there's an input image, an encoder that produces a code, and there's a decoder. But now this scaling factor is, or gain as it's sometimes called, is produced by another autoencoder that takes as input a segmentation mask. So the segmentation mask can be produced by another neural network that, say, detects people. It can be crafted by hand or produced in any other method. It's compressed by the mask encoder, produces some codes that will be transmitted, and these are then decoded to produce this gain factor, which is used to adjust the quality separately at each spatial position in the image. And this whole system is then trained end-to-end using a loss function that also emphasizes the foreground over the background regions. Here you see some results. We have in blue, we have our approach versus the baseline neural compression method in red. And you see separately the foreground and background curves. And what you see is that for the segmentation AE, i.e. this semantic aware method, the background is a little bit worse. The curve is lower. But the foreground is dramatically higher, and even as you reduce the bitrate, as we move to the left, we see that the fall off in PSNR, in the visual quality, is actually limited. All right, so then we can talk about GANs, or generative adversarial networks. And before we go there, I need to explain this concept of distortion and perceptual quality and what the difference is. So distortion means the difference between the input image and the reconstruction produced by the decoder. Perceptual quality, on the other hand, just measures how visually pleasing is an image. Does it have artifacts? Is it blurry? Or is it a crisp, nice-looking image? Now, we see on the left here our original image, and to the right in the second column, we see what could be output by a model that's trained on rate and distortion. This is only trying to spend as few bits as possible while making it look as similar as possible to the original for every single pixel. So distortion is good, but perceptual quality can be bad at low bit rates. You get blurring and other kinds of artifacts. If you were to optimize instead rate and perception, you would get something like this. You get a crisp, nice-looking image, but it has nothing to do with the original input. So what we want to do is we want to balance these three factors: minimize the bit rate, minimize distortion, or make sure it's not too big so the output looks like the input, but also optimize perception. So you can see, I hope it's visible on the stream, but you can see that this image on the right has much more fine texture details than the rate distortion, the second column. So how can we achieve this? Well, we use something called a GAN, a very well-known generative modeling technique. So it works like this. A GAN has, again, an encoder and a generator or decoder, as well as a prior that's used to compress the latents. But unlike a simple rate distortion optimization procedure, what happens here is that there's a third neural network called a discriminator. And this discriminator is tasked with classifying whether its input is an image from the data distribution, not compressed, shown on the top, or it's something that is output by the decoder of a compression system. So this discriminator is going to look for artifacts and other clues that the image being produced is actually not a real image, but a compressed one. On the other hand, the task of the rest of the system in blue is to fool the discriminator. So it's tasked to output an image that the discriminator cannot tell apart from a real image. So in this way, the system will try to produce realistic-looking outputs. And here we see some results. We have here in the center a raw image, uncompressed, with several close-ups. On the bottom, you see a state-of-the-art image compression system, BPG, that's also used in the HEVC video standard. And you can see quite severe artifacts. Whereas on the top is our GAN-based approach at, in fact, a lower bitrate, slightly lower bitrate than BPG. And you can see that although the details aren't exactly the same as in the center row, these images actually look much better. So that's what a GAN can do. All right, so then we get to our work on taking all of this research and actually deploying it on a device. So this is early stage work, but we're very excited to show you a demo of neural decoding running in real time. So what we have here is a video in something very close to 720p HD format. What we do is we encode it using encoder neural network trained on a large data set, and we use something that we call parallel entropy coding to compress the latent variables produced by the encoder neural network into a bit stream. This is all done offline and not on device at this point in time, although in the future we hope to do that. And then on the device, on a Snapdragon 888 mobile platform, we have two components. We have the parallel entropy decoding running on CPU, and we have the decoder neural network running on an AI accelerator. And we've achieved 30 plus frames per second using this approach. So how did we develop this? Well, first I should say that we limited ourselves to iframes only. So this is not a competitive system yet. Iframe compression is clearly suboptimal, but we wanted to start with something very simple. So we take our iframe compression model, consisting of encoder, entropy coding, decoding, decoder, all in floating point format. And we then did some architecture refinement to produce a more efficient decoder architecture. We also developed this parallel entropy coding algorithm, which is actually something that's not possible for classical codecs to parallelize this, but for neural codec, it becomes possible to develop parallel algorithms for entropy coding. That also reduces a very important bottleneck. Then we use the AMAT quantization and the model efficiency toolkit available at the link shown in this slide to do the quantization of this architecture, go from floating point to 8-bit, using something called quantization aware training, which produces then this highly efficient network that we deploy on device. All right, so we have for you a video, and I hope it will start playing now. Yeah, there we go. So here you see it on an actual phone. You see that the video is, it's probably not visible on the screen, but this is a very high quality video, runs at roughly 30 FPS, sometimes quite a bit higher. Bitrate, if you're familiar with these numbers, this is not a good bitrate. Again, that's because we're deploying an iframe compression model. But the good news is that the bitrate is actually similar to our floating point model. It's a little bit worse due to the quantization, but the gap is quite minimal, which gives us hope that as we deploy our P-frame and B-frame codecs, we will achieve very competitive bit rates using this approach. All right, so then briefly a couple challenges that are still ahead for the mass deployment of neural video compression systems. So the first one is computational efficiency. So neural networks, they are great at lots of tasks, but they're notoriously compute intensive. And the AI hardware that Qualcomm is developing can certainly go a long way in addressing that, but there's still going to be challenges in that area. And as our research on this neural video coding demo shows, it is possible. It's probably possible to make this efficient enough, but there's still work to be done there. The other is perceptual quality. So we've shown some proof of concept that at least for image compression, using this GAN technology, we can really improve the perceptual quality a lot. But there's still work to be done, even in the image case, and certainly in applying this kind of technology to videos, making the results temporally consistent, and using really high quality perceptual quality metrics as well for training. There's still work to be done to improve rate distortion performance, the core measure of correction systems. We already have very competitive results, and if you look at the rate of improvement over the last 2 years as we've been working on this, and as the field more broadly has worked on this, it's really a rapid rate of progress. So we're very optimistic about this. And finally, there's not necessarily a challenge, but there's a lot of work to do to bring this technology to new modalities like point clouds and other types of data. So with that, I'd like to conclude and do a quick recap. So we've seen that AI-based compression has the potential to more efficiently share video and voice across devices. We're conducting leading research and development in end-to-end deep learning for video and speech coding. And we're solving implementation challenges and demonstrating for the first time a real-time neural video decoder running on the smartphone. Thanks, and thanks for your attention, and I'm happy to take questions.
Thank you for the great presentation, Taco. Lots of questions have come in. So we'll try to get to those, as many of them as we can. Please keep submitting them in the Q&A widget. And so with that, let's go to the questions. So the first one, the neural codec work you presented shows great compression. How does the compute complexity and power compare to a conventional codec implemented in hardware?
Yeah, that's a great question. It's also fairly difficult to answer because the conventional codecs are not run on a CPU where you could just compare flop counts or something like that. We can also not easily compare wall clock time because our system runs on a neural processor, whereas the classical codec runs on special purpose hardware developed for that codec. But what I can say in general is that neural compression systems, neural networks in general, are very compute intensive, and there's challenges with respect to compute and also energy usage. But as our demo shows, these are surmountable challenges. So we're already at a stage where we can run an iframe only system on a device. The P-frame and B-frame models are somewhat more complex, so they use more compute. So there's still challenges there, but it seems likely that with more research, this will be feasible.
That's great. For your instance adaptive video compression, how would this work in practice? Would someone like Netflix have a neural codec per movie or episode of a series?
Yeah, that's a great question. So that's indeed how it could work. So in some use cases, like say if you're using your smartphone to record something, it's unlikely that your phone will have the compute capability to fine-tune a whole compression model on this particular video. But a party like Netflix, they already spend humongous amount of compute to find the very best possible compression for every single video they have. And so with this technology, they could actually fine-tune a codec for a particular video, and then transmit that codec before they send the video, and then send the video using the optimized codec. You could even do this on a more fine-grained level, where you say each clip of the video is corresponds to its own codec, meaning its own set of neural network weights that are fine-tuned for that particular clip.
Great, thanks, Taco. So the next question, I'm assuming that the encoder and decoder of a neural codec are paired from the same AI model. For mass deployment, do you expect there to be a single dominant neural codec, or would there be a lot of variants?
Yeah, that's a great question, and I guess time will tell. But there is, as this adaptive compression work shows, there's substantial benefit in having a different codec for each video or each type of content, like sports videos or something like that. So there's benefit to that in terms of rate distortion. But of course, there's also deployment challenges, because if you have a codec, well, if you develop a new codec, you have to make sure it runs on every possible end-user device. And although in the future we expect every device to have some kind of neural processing hardware, they will not all be equally powerful. So you might have to then develop codecs with different levels of complexity for different devices, which could be somewhat of a deployment challenge. Again, for a party like Netflix that has a lot of time to spend on for each video, this is probably going to be fine. For other parties, it may not. But so there could be a mix. There could be some neural codecs that are standardized and that everybody can use, and that every device maker will benchmark against. And then there could be specialized codecs for use cases where you compress once and you deploy, you transmit the video many times.
Okay, that makes a lot of sense. Next question. For new modalities like point clouds, how would a neural codec be developed, and why would it be easier to develop than a conventional codec?
Yeah, good question. So in general, what you'd want to do is you want to use a neural network architecture that's adapted to this type of data. So if you think about images, they have a spatial structure, X and Y directions. Image content appearing in one location will tend to also be able to appear in other locations. So these networks are based on an operation called convolution. Convolutional networks are sort of the bread and butter of neural networks for images. If you had a point cloud, well, that's a set of 3D points, and there are actually point cloud neural networks as well. So those are adapted to this kind of data where the order of the points doesn't matter, but their three-dimensional spatial configuration is what's relevant. So there are specific architectures for that that we can use. And why would it be better? And the reason is that if you develop a classical codec, that's very labor intensive. You have a very complicated code base, highly optimized, and an expert will make some change to this code base, and then run a very extensive set of experiments and analyze the data, and then decide whether to keep this change or not. And you repeat this many, many times. So it's very labor intensive. Whereas for the neural compression approach, a lot of that work is essentially automated in the training process. We use very powerful GPU clusters to train this model, to make many, many changes to the compression model, and essentially benchmark that on the whole data set all the time. And this process is just much faster. So as we've seen in our work in the last few years, this tends to give you results much quicker with far fewer researchers required.
Great, thanks for the explanation. The next question, and actually we've gotten a bunch of questions around how do you, the metric for quality and how do you measure that? So is there any specific metric designed to evaluate quality of the neural codec? And I guess your general opinion about evaluation of the metrics.
Yeah, well, evaluation is a very tricky subject. The metric that's been used almost universally across the classical codec community and also all neural compression methods are benchmarked again is PSNR, which essentially measures the difference between the reconstructed value of each pixel and its original value and aggregates that in a sensible way. So this is a pixel-wise metric. And what you can know is if your PSNR is very high, then certainly the image or video looks very much like the original. But human visual system is not sensitive to various kinds of changes that PSNR would pick up on. So for example, if we use this GAN-based compression system, we will allow for some higher distortion, meaning on a pixel by pixel level, the output can be quite different. But the changes may actually be quite imperceptible to a human judgment. So your PSNR will tell you this is not great, and actually subjective human judgment says it is a great reconstruction. So in that case, the ultimate metric that we believe in is to actually ask a panel of human experts to judge the quality and the similarity. But this is, of course, very labor intensive. You can only do that once in a while, and certainly you cannot use it during training. So then there's a whole field of research on different kinds of quality metrics for images, for video. It's rather complicated. I think there isn't any perfect metric, but we are certainly looking into this and seeing if there's any metrics out there that are better than just plain PSNR or MSSIM, and in particular ones that we can use for training, because some of them, they work quite well, but they are not easily differentiable, so we can't use them during our training process.
Great, that sounds like a problem for the whole industry to keep trying to tackle.
Absolutely.
Next question.
Yep.
Can these methods also be used to remove noise and or increase the resolution?
Yeah, that's another great question. We actually have a line of research on that. I haven't spoken about it today, but it's certainly a promising direction. So these generative models that I've been talking about, often they're conditional generative models. So conditioned on some piece of data, say text, you generate some other data like speech. You can also do that by conditioning on a low resolution image and trying to predict the high resolution version. Or you can condition on the output of a compression system, which may have artifacts and blurriness and so on, and try to generate a higher quality artifact-free version of that. So there's a lot of research on that. We're also involved in it, and I think this may well end up being part of the solution in the end.
All right, try to squeeze in maybe two more questions. Is the speed of overfitting for encoding the same as encoding using regular codecs?
Oh, that's a great question. So for most of the codecs that we've developed, the ones that don't use this instance adaptive technique, don't use this overfitting, our encoder is actually way faster than a typical state-of-the-art encoder. The reason is our encoder is just a feed-forward computation. It's a lot of multiplications and additions, but it's just one simple computation, whereas compression using a classical codec typically involves some kind of search procedure over various prediction modes and other switches. So that a lot of the gains in compression among classical codecs has come from increasing complexity at encoding time. So more and more compute thrown at the problem. And essentially what we're doing by this instance adaptive technique is also throwing more compute at the problem. And so certainly the cost of compressing using instance adaptive technique is a lot higher. But in our paper on this topic, which you can find online, we have a plot showing that we on an equal compute basis, we are actually doing better. So I would say that yes, we're on a similar level in terms of compute for encoding, that is.
Great, thanks, Taco. I think that's probably a good point actually to stop this since we're a little over time now. I want to reemphasize, probably good to check out some of the papers that we listed in the presentation for much more detail and depth on some of these things. But on behalf of Qualcomm and our presenter, thank you for joining us today. The webinar will be available on demand, and have a great rest of your day. Goodbye.